Extreme value theorem. Now that we feel comfortable solving for local extrema, we can go further and determine where absolute extrema occur. Remember, for absolute extrema, we must compare all extrema within the given interval, as well as the endpoints of that interval. The extreme value theorem states, if f of x is continuous on the interval closed from a to b, then f of x must attain an absolute maximum and minimum on that interval. Which of the following graph or graphs meet the criteria for the extreme value theorem on the interval from -2 to +2, containing both endpoints? Circle your answer. For those graphs that do not meet the criteria, explain why. Well, let's actually examine each of these to determine whether or not the extreme value theorem is satisfied. So for this absolute value function, we are evaluating it from -2 to 2. And we can clearly see that the absolute value function is continuous within this interval. Therefore, f of x must attain an absolute max and min on that interval. We'll definitely see the absolute min right here. And then the absolute maximum values will probably be occurring at the endpoints. So this one definitely meets the criteria. Now let's look at this function over here. We're going from -2 to 2, and the first piece of the extreme value theorem is that it must be continuous. Well, we can clearly see that this function is rational and has an asymptote being the y-axis. So this one is not continuous. So it does not meet the criteria for the extreme value theorem. Okay, now let's look at this one down here. We're going from -2 to 2, and the extreme value theorem says that if it's continuous, which it is, then f of x must attain an absolute max and min on this interval. Well, we definitely can see an absolute min. The absolute max is probably going to occur way up here at -2 when the function ends up getting there. So yes, this one definitely fulfills the extreme value theorem. And now let's look at this function. First, is f of x continuous? Yes, it is. On the interval from -2 to +2, it's going to be up here somewhere when the graph gets to +2. It'll have an absolute max. That'll be this endpoint over here because it's definitely higher than this local maximum that we found, and it will have an absolute minimum right here. So this one also satisfies the extreme value theorem. And here are the solutions to this extreme value theorem example. They do match exactly what we said. We circled the first one, this third one, and fourth one because they fulfilled the extreme value theorem, whereas the second one in the upper right-hand corner is not continuous, so therefore it doesn't satisfy the theorem. Let's take a look back at a previous example. Find the absolute extrema for f of x is equal to x to the third minus 6x squared plus 9x plus 1 on the interval from -1 to 3.5. Well, we found that this function had a local minimum at 3, 1 and a local maximum at 1, 5. Now, to find the absolute extrema, we need to compare these with the endpoints that have been provided in our interval. So if we substitute our endpoint values into the original function, we'll have -1 cubed, -1, minus 6 times -1 squared. That's going to be +1, so -6, plus 9 times -1 will be -9, plus 1, and we will end up getting -15 for the function evaluated at -1. And now we have to do the function evaluated at 3.5 or 7/2. And if we evaluate that, we'll end up getting 1 7/8, or 1 875 thousandths. Now if we compare all these points and we look for the largest and smallest y values, we had the local minimum at 3, 1, and we found that the endpoint is -1, -15. That is our absolute minimum value because it is much lower than this one. And then we have the local maximum at 1, 5, and the other endpoint at 3.5, 1 7/8, or 1 875 thousandths. And we can clearly see that these two are the absolute minimum and maximum values, respectively. Let's try another example. Find the absolute extrema for the function f of x is equal to 3x raised to the 2/3 power minus 2x on the interval from -1 to 1. We can begin by taking the derivative of f of x. When we do that, f prime of x is going to be equal to 3 times 2/3 is 2, times x raised to the -1/3, because 2/3 minus 1 is -1/3, and then minus 2. And then if we set this equal to 0 and solve, we will get that x is equal to 1. Well, that's also one of our endpoints. It's good to note that. And then we can also see that because our derivative has a negative exponent, that moves the x to the denominator when we rewrite it. So we could also write f prime of x as 2 over x to the 1/3 power, or you could write it as the cubed root of x, and then minus 2. We can also see that x equals 0 will provide us with an undefined answer. So that is also a critical value to test out. Next, use a sign chart to determine if there is a local extrema at x equals 0. Note, because we found that x equals 1 is one of our endpoints, you don't necessarily need to include it on your sign chart. If you would like to, you can, but I would recommend putting the 1 there and putting the closed interval or stopping your number line so that you don't select another number greater than 1 to substitute into the function, because we're only evaluating it from -1 to +1. And then if we test out a value such as 1/2, or even better, because we're dealing with a cubed root, 1/8 is a perfect cubed root between 0 and 1, we can determine that we would have a positive value here, because the cubed root of 1/8 is 1/2. 2 divided by 1/2, because we had 2 over x to the 1/3. So we had 2 divided by 1/2, which is going to be 4. 4 minus 2 is 2. That's how we get this positive value. And then if we did -1/2, we would have -1/8, because that's the cubed root of that you can do. 2 over -1/8 will give you -1/2. 2 divided by -1/2 will be -4. -4 minus 2 will be -6. So you will have a negative value here. So again, 1/2 or 1/8 and -1/8, when we substituted them in there, we ended up getting -6 and +2. So that's how we got our minus sign and our plus sign on our sign chart. So we can clearly see, because we have a decreasing and then increasing function here, 0 is considered to be a local minimum value. The last step is to find the respective y values at each local extrema as well as the endpoints. So for that local minimum value that we found at 0, if we substitute 0 into our original function, we get a y output of 0 also. So f of 0 is 0, and then we also have to find the function values at our endpoints. F of 1 is going to be 1, and f of -1 is going to be +5. And from here, since f of 0 is 0, that's our smallest y value that we have here, so it's our absolute minimum. And then f of -1 is +5, so that is our absolute maximum.